we have a graph of g of x. We want to sketch the graph of its inverse on the same grid. So the first thing we're going to look at are points. We have the point here, negative 4, 4. That means on our inverse graph, we're going to have 4, negative 4. I'm going to draw y equals x, the diagonal line, right across there. And does it make sense that negative 4, 4 will go to 4, negative 4? Does that look like it's gone straight across that line to that point? And the next point that we have on our red graph is the point negative 1, negative 1. Well, that's interesting, because those coordinates are the same. When we switch them, we're going to get negative 1, negative 1. I'm going to just connect those lines for now, and we can maybe see that that first line is a reflection over the line y equals x. Our next point on our graph is 1, 3. So switching the x and the y, we get 3, 1. And finally, the point 3, 2, it changes to 2, 3, and it crosses back. So a couple of things to note on here. Where does the blue graph and the red graph intersect? Well, that happens at points that are on the line y equals x. Because any point that's on the line y equals x have the same x coordinate and the same y coordinate, like negative 1, negative 1. In fact, that's what y equals x means. Every y coordinate equals the x coordinate. And if you switch them, it wouldn't make a difference. So when we're graphing these, one of the things we want to be careful with is that whatever points are on this diagonal line, those would be points that stay the same. Part B of this question says, is the inverse a function? So one of the things that you've learned in the past is when something is a function or not. Do you recall how to check that? What did you use to find out if something is a function or not? And how can I use it to say that here the red graph is a function, but my blue graph is not a function? Do you remember? Something called the vertical line test. So you draw a vertical line. If you take that vertical line and you move it across, if it's a function, it can only hit your graph one point at a time. So watch as I go across the red one. See, my black straight line is only hitting the red graph in one place all the way along. But if I do the same thing with my blue graph, there's lots of places where at this point, you see that vertical line hits my blue graph twice. I even have a place, I think, over here. If I move it further, it hits the blue graph 3 times. If it hits the blue graph more than once, and it only has to happen that it hits the blue graph more than once in one place, that means that it is not a function. So for B, so it is not a function. Now, as part of an explanation, we can say it does not pass the vertical line test, which means some x values have more than one y value. And that's what makes something not a function. If you have more than one, you put in an x value, and you get more than one possible answer for your y value, it's no longer a function. Okay? And sometimes when I'm introducing functions, I make the function machine. And the function machine says you put in a number, so throw in a number, 4. You put in 4, something happens inside the machine, and it pops out a 15. Okay? And so if you put in another number, you put in 2, something happens in the machine, out pops a 3. And we might have a challenge. Can you figure out what's happening inside the machine? You can put in more numbers to check. Now, if you put 4 in again, it'll always pop out 15. That's what makes it a function. It always does the same thing, right? If I put in 5, out would come 24. And if I put in 10, out would come 99. Any ideas what that function machine is doing? Amy? Yeah. So this one is just times by itself minus 1, and that's a function. So we use function not only in math, we have other things like with machines, they function in certain ways. Your calculator functions, it does something. And when something functions, what it means is it's always doing the same thing. So let's say you want to have a machine, some sort of robot that makes you something. Maybe it's making something out of plastic, and you put plastic into the machine, and then blip, 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 out comes a Nerf gun, right? And so you've got a Nerf gun making machine. You put in plastic, always what comes out is a Nerf gun. You would say that your function isn't your thing wouldn't be functioning if one day you put in the same amount of plastic, and instead of outcoming a Nerf gun, comes a plastic puppy. And you're like, what? And the next time you put in the plastic, and out comes a math test. This would be like disastrous, right? So it's something different is coming out each time. This is what this vertical line test is showing, that when I put in this x value, 3 different things come out. It's not functioning, and that makes it not a function. It is still considered a relation. That's the word that we would use for anything that you can put on a graph is called a relation, because there's a relationship between the x and the y's, but it may or may not function necessarily. So now state the domain and range of the function and its inverse. So in part C here, I'll do the original one in red. I'll use set notation. So our smallest x value is minus 4. Our biggest x value is 3. Oops. So negative 4 is less than or equal to x is less than or equal to 3. And for our range, our smallest y value is negative 1. Our largest y value, it goes all the way up to 4. This is the domain and range of our red graph. And now when we look at the domain and range of our blue graph, again, we can look at the graph and say, now what's my smallest x value? It's minus 1. And my largest x value is 4. My smallest y value is negative 4. My largest y value is 3. And what do we notice? Well, the big idea with inverses is that you're switching the x and the y's. Now, if your domain is your x values, and you switched x and y, can you see that your domain becomes your range, your y values of your inverse? And your range, which were your y values, become your x values, the domain of your original function. Okay? Some language. Okay? The language we use here is sketch the graph of its inverse. It's not saying sketch the graph of the inverse function. Okay? And when we look at our notation that we did before on the part that we highlighted right at the beginning, on this that we highlighted right at the beginning, you'll notice right here, that notation is for the inverse function. So we can only use this notation, f with a minus 1 of x. That notation is only if the inverse is a function. So that'll be something that we see coming up as well. Okay, questions for practice, for example, 1 are 4 and 9.